Okay, so let's pick back up there. So now you've learned about laminar versus turbulent flow and the difference between them. Now, hopefully you've learned a little bit about how do we know which one is which. Well, the truth of the matter is we don't know for sure if flow is laminar or turbulent unless we actually can look at it. So I'm hoping you saw some videos maybe where they've injected a dye or maybe some smoke into, if it's air, maybe you inject smoke into the air so you can see how the fluid particles are moving. If it's a liquid, you probably inject some kind of a dye tracer in there. If you're standing beside a stream, you can throw some paper or some confetti on the surface of the stream. Excuse me. And watch how those particles, those tracer particles, move. Do they get all scrambled up, or do those particles move in a straight line? That'll tell you whether you've got laminar or turbulent flow. Laminar is where all the particles move parallel to one another. They all move in straight lines. Turbulence where all the particles kind of jumble up and they go crazy and they move around very chaotically. How do we know? Well, again, we have to see it either with a tracer or dye or smoke, something like that. But we can predict laminar versus turbulent flow with a quantity we call the Reynolds number. All right, the Reynolds number. Remember from Chapter 7 we saw this guy. This is the density of the fluid that's flowing, the speed of the fluid, times some kind of a characteristic length. Diameter normally works. We're going to talk about this in a second. Divided by viscosity. Now, for conduits, for completely filled conduits, a Reynolds number less than about 2300, it's normally a pretty good assumption that you're dealing with laminar flow. And so the flow is moving along nice and steady, and all the molecules are going to stay pretty much moving parallel to one another. If the flow is greater than, and you'll find sources that will differ on where the boundary actually occurs, but in general, if you're dealing with flow over about 4,000, it's a pretty good assumption that you're dealing with turbulent flow. In between these two, what do we do with it? Well, we got to guess. We either have to guess or we need to be able to actually see the flow and actually try to inject some kind of a tracer that we can observe its behavior. We're not sure in between. It's a pretty good bet. You get over 2300, it's a pretty good bet it's turbulent, but it's possible it can still hold together in a fairly laminar fashion, especially if it's long, straight piping. It's just hard to say without actually looking at the flow, which in most cases is impossible to do. If it's flow in a piping system, it's a completely filled conduit, you probably can't look at the flow and see. But the good news is, for our purposes, we're normally going to be dealing with situations where we're really trying to move the material very quickly, so the speed is very high, and therefore the Reynolds number ends up being very high, and so normally we're dealing with turbulent flow. Or we're dealing with a situation where we're really trying to keep the flow moving slow and steady in a controlled fashion, so we'll probably be moving at a slow speed, and we're most likely dealing with laminar flow. It's normally pretty obvious. We can talk a little more about what do we do if it's in between, but it's pretty rare that we'll encounter something in between. It's normally one extreme or the other for our purposes. Okay, so let's just assume that it's going to be pretty obvious. We're not going to deal in that transition stage in between too often for right now. By the way, remember this, there are a couple of viscosities. We talked about this early in the class, and I don't ever remember the difference between the two. Right? You've got mu, and you've got this other one we normally use the letter nu to represent that one, where nu is the ratio of mu and the fluid density rho. Okay, and so That's the reason you see the Reynolds number can be written as speed times a characteristic length, normally diameter, divided by this other viscosity, not specific volume. Okay, sorry, I know that's another V-looking shape. That's kind of confusing, I get that. But it is another viscosity term. At this point, you should be able to look at your units and your dimensions and figure out which quantity you're dealing with, whether you're dealing with viscosity or specific volume. And if not, you really need to start getting good at looking at your units and dimensions to try to figure out what quantity you're dealing with. You've got to do that moving forward, guys. Okay? And here I've got, so just continuing off my slides here. Again, trying to stick with what we normally do in class, try to not get us too far off. But you can see I've basically already stolen this thunder, so let's keep moving. Again, these values are approximate. It's only a prediction. In the most extreme cases, if you're really careful, you have nice smooth tubing, you keep the flow moving in a very straight line, you can have laminar flow at really ridiculously high Reynolds numbers, but you really have to do that intentionally. It doesn't happen accidentally. If I've just got fluid flowing through some commercial piping system, if I've got a Reynolds number over 4,000, the piping system's going to be rough enough and there's going to be twists and turns, you're going to have turbulent flow. Okay? Anyway, that's plenty on that. That's not something we really have to be super concerned with. We just need to know what's the Reynolds number. Is it above 4,000? We're going to use a turbulent model. If it's below 2,300, we're going to use a laminar model. If it's in between, we may have to guess and check. Excuse me. Get some water here. Okay. Now, this D, this hydraulic diameter, a characteristic length as I've been calling it, that's a term you'll hear later on, especially in heat transfer. You'll hear that term, characteristic length. For us, this characteristic length, when we're talking about conduit flow, it's normally this hydraulic diameter, right? And you can see here there's a formula for hydraulic diameter. That's 4 times the cross-sectional area divided by the wetted perimeter. Now let's reposition pages here. I think I'm going to start dealing with loose leaf paper or pull sheets out. Okay, here we go. All right, so hydraulic diameter is 4 times cross-sectional area divided by the wetted perimeter. Okay, so if I have, let's say I've got some kind of conduit that's rectangular in shape. Okay, so let's say I've got dimension here M, and let's say I've got dimension here, I could say N, but let's use something different. We'll say length, L. Okay, so 2 different dimensions there, and I've got fluid flowing down that conduit there. Okay, so cross-sectional area of that conduit is going to be M times L. Right? Now the wetted perimeter, what the heck is that? Well, that is the length in contact with the fluid. So you go around this cross-sectional area and you add up the length, all of the lengths that are touched by the fluid. If the conduit is completely filled, the entire length is going to be wetted. It's going to be in contact with the fluid. So that is M. And so starting here, you're going to go M, L, M, L. Right? So it's M, L plus M plus L. Right? M on both sides, L on both sides. So this is 2M plus 2L. So that means the hydraulic diameter is going to be 4 ml divided by 2m plus 2l. Okay? That's for any rectangular conduit. Notice if m and l are the same quantity, right? The the hydraulic diameter just ends up being, I've got 4L squared over 4L. That's just L, which is also M. Okay, so if it's square, right, if the conduit's square, this length is just the length of one side. Now we also say down here, normally we're going to deal with circular pipes. We've already talked about why. Circular pipes, that hydraulic diameter is just simply the diameter of the pipe, and we can see that pretty easily. Right? 4 circles, same principle. I'm going to go through this pretty quick. Okay, so that's 4 times the cross-sectional area. That's pi r, let's say pi d squared over 4. Let's deal with diameter here. Divided by the wetted perimeter. Well, the wetted perimeter is the circumference of the circle. That is just pi times diameter. So 4 pi d squared divided by 4 divided by pi d is just d. For circles, hydraulic diameter is just equal to the diameter. Okay? So, most of the time we're going to deal with circular pipes. Most of the time our hydraulic diameter is going to be simply the diameter of the circular pipe. Why do we care? You guys know me, I like to ask this question sometimes. Why, Steve, why in the world do we care? Well, again, I've tried to lay this out pretty hard at the very beginning. Estimation of the energy loss from this viscous flow is going to be different whether it's laminar or turbulent flow. Okay? And again, the Reynolds number, which is what we're going to use to predict whether the flow is laminar or turbulent, is going to be rho v this hydraulic diameter divided by the viscosity. This value will give us a prediction as to whether we're dealing with laminar or turbulent flow, because I need to use different energy models to try to estimate the loss associated with that. So, now this is, not sure why this is not displaying well on my tablet. Anyway, here we are. Normally when we're dealing with pipe flow, we're typically concerned with the pressure loss due to this viscosity, due to the viscous flow. Right? So that's what we're trying to quantify, is what is the pressure loss over a length of pipe. And I'm looking at my timer here. This is a good place to stop. My camera breaks these up into 15-minute blocks, and I'm just about 14 minutes. So I'm going to break this up to the next video, and we'll pick up here.